Okay, let's come back to engineering statics just to sharpen some brains because I found it's quite difficult to get my brain to work during holidays. So I found some, because it's been a long time, I have not practiced engineering statics. So I thought just bring two examples just to work it out step by step. And I found also it's quite useful if you can practice your bending moment shear force diagrams to do some hand calculations of them, and it helps you quickly spot and also checking others' work, as well as sometimes you checking your own computational models. Um, be able to quickly spot whether the bending moments are making sense to you. So yeah, with that skills, of course, you would need to practice it often. So let's get onto it. So for the first beam here, it's got a hinge here. When I see a hinge, that means I've got a bending moment here. It's going to be a triangle profile. So that is going to be the maximum of the bending moment here is PL over 4. And because it's got a hinge, so and it's also got symmetrical profile as well. So it's coming up to here. So in this case here, we can first work out this moment here is going to be PL over 4. That's 120 times 6 divided by 4. That is going to give you 180 kilonewton meters. That's your bending moment. And because it's symmetrical, so over here, and you can work out by using trigonometry as a 2 meters and a 3 meters here. And that gives you about 120 exact bending moments at this hogging moment. At the support here, pin support, as moment is 0, so you're connecting those 2 points and it forms a straight line, and you can work out your bending moment for this segment 8 meters here. At the center of the triangle is going to be 60 because you can use trigonometry, right? 60 in the middle, 120 at the peak, and that portion here, that is 60 kilonewtons meters. But what about here? So this is what we need to find out, right? The maximum positive moment at the tension face. So the overall distance, overall segment here, that is omega L squared over 8, right? So that is your 40 times 8 squared divided by 8. The overall gives you, and hang on, that's going to be 320 kilonewton meters. And you minus 60 because 60 is on top of it, and you only need the ones below, right? Remember there's a line here, right? You only need this portion here. So what is maximum here? So the 320 minus 60, that gives you 260. So 260, 120, 180, that is your bending moment diagram. All right. Moving on to the next one. This one is not so lucky because you need to get your reactions force first, otherwise it's a bit of difficult to draw bending moment diagram straight away. So based on statics, you can assume that moment, let's call it AY, and I'll call it BY. All right, AY and BY. You convert that into a point load, which is a 5 times 6 is a 30 kilonewtons, and acting a lever arm to AY is 3 meters, half of that. So moment MA at A point is 0. I am assuming the positive clockwise as positive moment. So that gives a 30 times 3 and a minus BY, you're coming to A, rotating to A. Your lever arm is 10 minus 10 BY is 0. That gives you BY is 9 kilonewtons. Alright, 9 kilonewtons. So respectively, your AY is 21 kilonewtons. Alright, so in this case here, we can draw our shear force diagram. Right? Let's get FSD first. So I've got 21. Let's say 21 is over here. and over. So I don't care what's happening in the middle just now, because I know at the other end my BUI is 9 kilonewtons coming up. Okay, let's say this is 9 kilonewtons coming up, and at this point here, that's where the UDL finishes. So at this point here, coming down, so I know it's going to be a straight line because nothing happens in here. So it's a straight line for my shear force, and I'm coming. Oh no, sorry, you don't need it coming up, but it should be a dashed line. And connecting these 2 points, see, that is my shear force diagram. I got 21 here, coming down to 9, straight line 9, coming up to 0. That's my shear force diagram. And then my bending moment diagram is interesting. So first of all, you need to figure out what is the this distance in here, right? And then what is this distance here? So we've got a few important locations, and we need to specify the bending moments, because this is a triangle. Sorry, this is rectangular, and we can just work out about the area, because the moment is the integral of the shear force. So we integrate that. So 9 times 4, that gives you 36 kilonewtons meters. All right, that's the triangle, 36 kilonewtons meters. That's your bending moment at this point. But what about here? So here we need to work out what is the distance in here. Okay, so without this, this should be a parabolic shape. All right, and this point here, this is where your maximum moment here. So this moment is a combination of this portion of a triangle plus this portion of the parabolic. This distance here plus this distance. So this distance, to get to know this distance, we need what is this distance here. So you can using trigonometry work out this is 1.8 and this is 4.2. Let's say this is 4.2, and so we can use trigonometry. So this overall length from here to here, that's 6. So 6 divided by 36, that is equal to 4.2 divided by x. This is your x, so we can work out your x is 25.2. And this portion over here, and that is your omega L squared over 8, right? That gives you 22.5. So the overall is combined together, right, is 22.5 plus 25.2 plus 22.5 gives 47.7. Here we go. That's your maximum bending moment as a 47.7, and this is the next to it as a 36 kilonewton meters. So this is how we solve the bending moment and shear force diagram. Sometimes we do need to work out the reaction. Sometimes we don't. Yeah. Thanks for watching.